The next talk is by Louis DiMauro from Ohio State. He's going to be talking about strong-field atom physics in the long wavelength limit.
Okay, thanks. Okay, well, I'd like to thank the organizers for inviting me here today, and certainly maybe I won't thank you to follow Seth's very animated talk. So as you can see, I am a messenger of Satan here, and what Satan wanted me to tell you about today is a very simple physical situation of what happens when an intense light field interacts with an atom, okay? And this has been a field that's been around for decades now. Theoretically, it's been addressed even longer than that. But I want to talk to you about one specific aspect of this that has kind of interested me now for quite a while in my group. And we like to understand how this physics scales, okay? We are interested in this from a purely fundamental perspective in terms of verifying theoretical predictions that have been around, again, for many, many decades, although experimentally they hadn't been realized, mainly because we didn't have the light sources. So we took off on a path about more than a decade ago of trying to develop light sources that would allow us to test this very basic interaction over a larger span of space. Now, when we started on this, which I'll discuss today, which is heading towards low frequency, and I'm particularly interested in trying to test the strong field limit of this interaction. I had no idea back then that, in 2010, I would actually have the opportunity as an experimentalist to address this even in the X-rays. I mean, that seemed like fantasy land in 2000. But it's here now, as you heard from Christoph. I won't talk about that today, but certainly part of our effort is trying to understand this physics at very high frequencies. But again, today I will limit myself to the low frequency regime and try to tell you about how one could establish conditions for what I'll define as strong field ionization, or other people call tunnel ionization. So our observables, well, the experiment is simple. I have an atom sitting in my vacuum. I shine this intense light on it. The light is typically low frequency, so the atom has no linear response to this light. And then what we do is we observe electrons, ions, photons coming off this atom and try to understand what's going on there. So that's the fundamental process. And what I'll do today is point to how that could enable some applications, which I'll end with today, in terms of doing spatial temporal imaging. Okay, so here's one place that it started for us, at least. So here's a calculation we did a number of years ago. And what you see here is, again, argon atom interacting with near-infrared light. Why near-infrared? That's where most of the ultrafast people have their amplified systems. They run at 800 nanometers titanium sapphire. So what you see here is a calculation, a time-dependent calculation that we did. So here's our reference field, and here is time. And what you see is the contour plot is just brute force solution of the time-dependent Schrodinger equation. The solid lines you see there are predictions of a simple classical model of what happens if I put a free electron in the field at different phases of the field and watch it propagate and look at its various classical quantities. Now, what's actually being plotted here is this process of high harmonic generation. So what I'm plotting as a function of time and frequency is the time at which the light is emitted, okay? So this is the recombination time of the emission of the high harmonic light, and it has the various quantities. You see, classically, there's some classical limit to this. This is the cutoff law that is used in strong field physics. And what I want you to see here is that the quantum picture kind of mimics, at least on a half-cycle basis, what the classical prediction would say. However, of course, there's all the quantum interference in this picture, and so that complicates things in terms of interpreting experiments. So now we do the same calculation, but now we keep the intensity fixed, and we just move the wavelength out to 2 microns. And now what you see is that the classical and quantum agree very strongly, okay? And this is important to us because this is the point at which this kind of semi-classical picture of strong field ionization is actually agreeing with the actual quantum system, okay? It also has some other important implications for us, practical implications. As I said, we measure charged particles of photons. The question is, if I could realize this scenario in my experiment of this strong field or semi-classical behavior, I've now reduced my quantum paths down to, say, essential states that perhaps will allow me to kind of push back from my detector in time what was happening at the very instant that the light was interacting with that atom. Okay. So, okay, I don't have the rather nice dance, although I could, that Seth had. But here's the cartoon of our semi-classical view of strong field physics, okay? This model's been around now for over 20 years, okay? And it's this simple picture of what happens in an intense strong field, and the strong field limit, is that ionization is best described by tunneling. There's the semi part of my classical. And then once that electron or wave packet is freed into the continuum, now I use my classical mechanics to describe what is happening to its motion. And in this cartoon, I'm just showing you one process, the process of high harmonic generation, where the electron is driven away, comes back, and recombines back to its ground state. This is a coherent process, okay? It emits a photon of higher energy than the fundamental frequency that's driving that potential, okay? Now, the picture you should keep in your mind is not that kind of half-cycle picture, but the fact that this goes on at 2 omega in my field, okay? So coherence builds up in this electronic wave packet. In fact, at this point, we can almost forget about the photons in a sense. This is really an electron interferometer, right? A coherent electron interferometer. And what we're interested in is kind of exploiting this nature to learn things about, say, an atomic or molecular system. So what do we know from this classical picture? Okay, from the classical physics then, you know, all right, it tunnel ionizes. The tunnel ionization rate is proportional to the amplitude of the field, not the intensity, and it's exponential in rate, okay? So my ionization is occurring on a sub-cycle basis, okay, with the via tunnel ionization. So now I can think about the electron as being born at different phases of the field by tunnel ionization, and at that point then the classical dynamics just dominates its motion. The electron propagates for some time and comes back. Some electrons come back and could interact again with the core. That's what that picture is telling you. So we have the initial phase, we have, yes? It's only a half cycle. Yeah. This was just to demonstrate harmonic generation, yes. So again, it's periodic, okay? At least for a single cycle pulse, okay? So we have different release times, different propagation times, and different return energies classically. All right, this interaction is responsible for the creation of high harmonic generation. Okay, without this interaction, you have no way of getting photons out of just the quivering electron. Okay, and it's responsible for the creation of high energy electrons. So let me just give you a scale. That quiver is much larger than the initial state. It could be anywhere from angstroms to tens of nanometers under the experimental conditions of which we study this. The energy the electron picks up, this pondermotive energy, could be anywhere from a photon energy to many times the binding energy of the valence electron. Okay? So these are very large quantities. And let's look a little bit at the scaling now. So initially, very seminal work by Keldysh in the early 60s. In Keldysh's formalism, he described the way of determining whether ionization would occur via tunnel ionization or multiphoton. He was actually not interested in that limit. He was just interested in the tunneling limit. And he came up with this dimensionless parameter, which I write, perhaps not very well, as the ratio of the optical frequency, the fundamental frequency, to some tunneling frequency. Or it's the optical frequency times the tunneling time, okay? And what you find is that this quantity gamma scales as the 1 over the wavelength and as 1 over the square root of the intensity, okay? Likewise, the pondermotive energy, which is just the cycled average kinetic energy of the free electron in the field, scales with lambda squared and linearly in intensity. So right away you see, at least in these two quantities, lambda is these quantities are more strongly dependent upon the wavelength than they are on the intensity. And this pondermotive energy, which is essential in this classical picture for getting the high energy particles out, then scales quite favorably as one heads towards mid-infrared wavelengths, okay? And why does it pick up more energy? Because it's spending more time in the field, okay?
Pondermotive potential, something like an A squared contribution? Is it coming from that?
Yeah, yes, it's coming from the A squared. It's just the cycled average kinetic energy of the free electron. Mm-hmm. Okay, the attosecond chirp, which is relevant to attosecond physics, which I'll tell you about, also has a favorable scaling. It's dispersion. So there's a funny concept here, right? The atom has a single atom has a dispersion associated with it. And what is that dispersion? Well, different phases lead to different return energies, okay? And so the wave packet, the electronic wave packet that's propagating is actually chirp. So it has a dispersion associated, which we call this attosecond chirp. And you find that that attosecond chirp actually scales as 1 over lambda, okay? And it goes as the square root of the intensity. All right, I want to focus on two particular scaling parameters that, again, were discussed by many people. I list some of them here in terms of attaining the strong field condition. So here I list what they call the bound state and continuum intensity parameter. Z1 is the bound state parameter. You should think about this as just a power broadening in the extreme case where the power broadening becomes as large as the binding, okay? And that's when Z1 is equal to 1, okay? And then this continuum intensity parameter is just the ratio of this pondermotive energy to the photon energy. So the condition for strong fields using this set of parameters along with the Keldysh is that the Keldysh parameter must be less than 1 and both Z parameters must be greater than 1. That is, for instance, let's look at the continuum parameter. The positive motive energy is many photons in energy. Okay? So the concept of photons becomes a bit lost. So let me plot these for you. So here's the typical situation. I start off with red photons, amplified red photons, and I increase their intensity. So what I'm plotting here is intensity versus frequency. The red line is when the continuum parameter Z equals 1. The blue line is when the bound state parameter is equal to 1. And where I want to be in the strong field regime is somewhere up here. So I raise my intensity. At some point, perturbation theory breaks, perturbation theory breaks down. The electron starts quivering significantly in the field, and I keep raising my intensity, and eventually I run out of snuff. Why is that? This is extreme nonlinear physics. The tunneling rate is exponential in the field. So at a certain point, I just deplete my initial state if I shine a pulse of intensity. And this arrow gives you a good idea with red photons, where with atomic systems, you kind of limit it in a regime somewhere between the blue and red line. Okay. Oh. But what we decided to try a number of years ago is that the wavelength is, in fact, a continuous knob that it will allow me to tune in whatever sort of ionization dynamics I want. And so what we do is we move from red into the mid-infrared. And now you can see at the same intensity, which for tunnel ionization is independent of frequency, so the rate should be about the same. Okay, depletion should set in at the same intensity. I now can reach this strong field limit by a long way. So in either case, this is what experimentally, technically we've done. We pushed our sources out to, say, 4 micron wavelengths, generating sufficient intensity to kind of study this physics. That's exactly right. In this picture, tunnel ionization is setting in above this blue line. So that's what we're trying to achieve. So to me, the strong field condition is realization of that semi-classical picture I showed you. Subcycle ionization followed by kind of simple quantum trajectories. So it's a bit of an intuitive picture, right? I'm arguing here that if you want high energy particles, just head to a lower frequency. And that's exactly what you see in this picture here. So here's photoelectrons from the single atom, in this case xenon, okay, being ionized at different wavelengths at constant intensity. And what you see here is as I move from titanium sapphire, which produces electrons on the order of, say, 100 volts, and move out to 4 microns, I get electrons in excess of 1 kilovolt. Okay? So fulfilling this, these conditions of these parameters are certainly being met in this picture here. But I believe they are, but the rate actually doesn't change much. The only reason the rate changes is because the duration of these different colors is slightly longer. Okay, we don't have complete control of that. But each of these are about 6 cycle pulses. Okay, let me show it to you in another way, a way that emphasizes the Keldysh view of what's going on here. So again, this is the same data, except instead of plotting this in absolute energy, I'm plotting these in units upon the motive energy. And now within this kind of invariant view, there's clear classical predictions of where these limits should lie. And plus, within Keldish's view, if my parameter gamma is greater than 1, I'm not in the tunneling regime, and as I head to smaller and smaller gamma, I enter this regime of tunneling. And what you can see is that at titanium, at red light, I see this kind of strongly modulated spectrum. This is the well-known effect of above threshold ionization that was known about since the 70s. And as I head to smaller and smaller gamma at longer and longer wavelength at constant intensity, you see my distribution starts looking like a very rapid decay followed by a plateau. Okay, this point of a break in slope is classically what you would expect if I don't allow the electron to interact with the core. If I just calculate the maximum energy at my detector from a quivering electron in a field, it turns out it's twice the spondomotive energy. If I allow it to interact with the core, like in that semi-classical picture, now I find there's a new limit due to the fact that the electron can elastically scatter from the core, and that new limit is at 10 UP. So now you can see my distribution goes from something that is multi-photon-like, I mean, I can count photons there, to something that is an unresolved spectrum that has 2 classical breaks, 2 UP and 10 UP. This is the electrons that are reaching my detector because they rescattered off the core. All these other electrons are basically have no interaction with the core. And okay.
All linearly polarized light?
This is all linearly polarized light. Yeah, thank you. That's an important point.
Why keep the intensity constant? I mean, you can probably get much higher intensity with the
Much higher intensity. But again, intensity is not continuous. Intensity is limited by depletion of the initial state. And since this is tunnel ionization, the window at which I can vary my intensity in the laboratory is extremely limited. Okay? Where wavelength in a sense is continuous. So this rescattering, the fact of this high energy electrons, have implications that I'll try to talk about for spatial temporal imaging. So let me show you now some additional proof. So that's the elastic scattering we just looked at from the electrons. Now the electron could be combined, emit a photon. That's your high harmonic spectrum. And here you can see the high harmonics coming off argon for different wavelengths, again at constant intensity. At red photons, I get a maximum from argon of about 50 eV photons, high harmonic photons, where if I move out to 2 microns, the limit is set now at 200 volt photons. And experimentally, this is what we observe here, this kind of strong lambda squared scaling. Let me tell you now about this ATO chirp, because this has implications in terms of generating short bursts of light, better and better bursts of light. So what I plot here is, again, just a classical quantity of what I call the emission time, the time classically the electron is back at the core, as a function of its return energy, or harmonic energy, as I call it. And here I plot this for 3 different wavelengths that we used in our experiment. And the slope of this line, so this is a time versus energy. This is a dispersion, okay? So that slope of the line is indicative, at least in this linear region, of the inherent atomic dispersion of the atom. And as you can see, as we move out to longer and longer wavelength at constant intensity, the slope decreases, so the wave packet becomes less chirp, And this means I can generate shorter and shorter at-the-second pulses by going out the long wavelength. So again, we went in the laboratory and tried to verify that. Initially, we just did this by theory, looking at the classical quantities, and back of that were quantum calculations. But eventually, we were in a position to actually go in and measure this chirp. So we know how, without any details, to do metrology, where we can get the spectral phase of each harmonic component using a technique called the rabbit. Okay, this is such a measurement of the spectral phase at different wavelengths. And again, if you just look at the kind of lines here, the slope is decreasing. And we see this 1 over lambda decrease in this atto chirp in this figure here. So long wavelengths are the way to go to make higher energy particles. Long wavelengths are the way to go to make shorter pulses of light. The downside is long wavelengths also lead to less effective scattering of the electron wave packet with the core. Okay, and that you have to overcome by other means. If you're interested in at-the-second pulses, you use the macroscopic term in order to coherently build up these dipoles, even though the single atom dipole is decreasing in strength. Hopefully, coherently, you can overcome that. And the Giller group has kind of shown ways of doing that.
What's the maximum number of photons we can get at, say, 100 eV, given, what we have high sapphire?
So, okay, there's been all sorts of demonstrations. Typically, at 100 eV, you can get anywhere, dependent upon your expertise, from 10 to the 6 to 10 to the 8 photons per shot. Okay. Yeah, you have, it's the macroscopic part you have to work on. Okay. The dipole is given by the physics I'm talking about today, the strength of the dipole. So how much time do I have? Okay. So let me now just show you one application of the strong field physics that is very current in our laboratory. And this is the idea of doing spatial temporal imaging with these electron wave packets. Okay? And there's many groups throughout the world, I list some of them here, that are working on this. You can see this was a cartoon for Nature. Okay, so here's the picture. Right? Let's talk about electron diffraction. Okay, conventional electron diffraction. You have a source of high energy electrons. Okay, they're plane waves, and you scatter them off some molecule of interest, and you measure the forward scattering of that electron, and from that you can determine positions within the molecule. Okay, and this is a standard technique. So now what I'd like you to do is take that picture and say, okay, I have this wave packet that is propagating, say, by tens of nanometers, coming back and rescattering off my core. Can I think of that in the same way I think about electron diffraction? And can I then look at the momentum of those electrons and determine the structure, determine the position of the nuclei in that molecule? So I just want to, again, kind of ground us in the idea of how a successful electron diffraction experiment is done. Okay? Typically, it's a gas phase technique. So molecules are induced in the gas phase. Okay? So they're randomly oriented. Okay? They use high energy electrons for a number of reasons. Okay? For one reason is they want to make sure that their collisions are high enough energy that they're core penetrating. So now they can describe the scattering amplitude as a sum of individual atomic emitters. Okay? And Second, since they're looking at the forward direction at very small angles, they want to make sure that the momentum exchange in the elastic process is large enough, because that will determine their spatial resolution in the experiment. So typically, in a good electron diffraction experiment, they get momentum exchanges on the order of 2 to 30 inverse angstroms. So they basically can get about a picometer precision in determining atomic position, and they can do this from simple systems to very complex systems, as long as they can be introduced into the gas phase. Without proving this to you a great deal, what we aim to do is take this conventional electron diffraction analysis from the momentum distribution that we measure from this interaction of long wavelength intense light with this molecule. So what we measure is some funny looking momentum distribution. We don't measure a differential cross-section directly. But there's an important connection that could be established between this and the differential cross-section that has been known for years, but has really been formalized in the last 5 years by Chi-Dong Lin at Kansas State University. And that's the idea that in this semi-classical picture, okay, the wave packet feels all the influence of the field. But the collision process, since it's so short range, is not influenced by the field. Okay? So I have this field-dependent part, the wave packet, and then I have the scattering off the core, and that's field-independent. So I should be able to deconvolute from my experiment differential, field-free differential cross-sections. If I can get field-free differential cross-sections from that data, then I just follow the prescription as defined by conventional electron diffraction. So we did this demonstration experiment a couple of years ago. I won't belabor what's going on here. But what you see here is the StrongField experiment done both on nitrogen and oxygen. Okay, you notice this is time here. Well, what's this time business in here? The time is the fact that this is the period of the light that we're using. Okay, so again, we launch a wave packet. The wave packet propagates. That time is about a half cycle. So that's the time axis here. The different points are different colors. So different colors mean different propagation times. And what we do is we analyze that momentum distribution at fixed energy, okay, by our deconvolution method. And we extract differential cross-sections. Once we have that, we can then extract time-dependent bond or atomic positions or bond distances. And what you see here is that for nitrogen, you see the equilibrium value of both the neutral and the ion. You see our measurements here seem to reproduce that reasonably well, although we can't distinguish this small change in bond distance. Here for oxygen, though, because the equilibrium values are so different, we do see values in our experiment that seem to correspond to the fact that now the system has relaxed to the ion. But even more so, what we're claiming is that what's happening here is we're actually seeing the motion of this vibrational wave packet. So in this experiment, we estimate that we got about 5 picometers of atomic position. Okay, this is a direct measurement of position. And we have about a few femtosecond time in resolution.
So oxygen and nitrogen are complicated orbitals. What about hydrogen? Do you do those experiments?
No, because the elastic scattering of hydrogen would be small and real difficult.
Too tightly bound?
Just the because the cores are so small that the elastic scattering cross section is small. I mean, it's something as we get better at this, perhaps we can try. But for the first one, it certainly wasn't. So I'm going to end here. Let me just say, make two more comments on this. So what I just described to you, what we have already demonstrated, is the fact that it looks like this interaction of an intense field with a laser allows us to extract cross-sections. And the way we extract that cross-section is very similar to conventional electron diffraction, where we extract the differential cross-section as a function of angle from this momentum distribution. But we also realize that our wave packet is very broad in energy, okay? It ranges from 0 out to 3 times the Ponder mode of energy classically. And for our type of experiments at long wavelength, that Ponder mode of energy is 100, 200 volts. So we have collisions from 0 to about 500, 600 volts. And in that case, we might be able to extract the differential cross-section, but as a function of energy. And if we can do that, which I wouldn't be standing here telling you if we hadn't been able to do this, we might be able now to connect what we observed directly to a Fourier transform in the position. So I will end here and just let me acknowledge the group here. I will. There they are. So, okay, the people who pay for this work, and I just want to acknowledge Kazmin Balaga, Junlang Zhu, who's doing theory with us, and Kai Zhang for working on this imaging stuff, and Pierre Agostini at OSU and Qidong Lin. So thank you for your attention.
We have time for a few questions.
This is probably a naive question. You're making an analogy between electron diffraction in the regular sense and when the electron that is just been exited or pushed out of the molecule.
Mm-hmm.
And then you say about the energy distribution. And, but you mentioned one thing that may be relevant, but correct me if I'm wrong, that the electron that has just been pulled out of the atom has a distribution in k-space also.
Mm-hmm.
While in the regular or conventional electron diffraction, the k direction and momentum of the excitation electron is very well defined.
Is very well defined.
The upcoming diffracting pattern would be influenced by the fact that you have a superposition of 20 k-space.
So that momentum distribution that we measure, right, is composed of different k. So the way we do the analysis, the analysis I showed you, is to restrict ourselves so we know how to deconvolute this distribution to a very small range of k. Okay? However, the problem for us is that then we have to know the ionization rate, the tunneling rate, as a function of angle. Okay? For simple molecules, we can do that reasonably well. But if we have any hope of applying this to more complex systems, we can. So this idea of utilizing the broad-banded spectrum is much more attractive to us right now. And I should also mention so how we envision these experiments in the past, in the future, is that what you'll do is excite something in the system, and then come in with this pulse and record the image, okay? And then do a pump probe sort of experiment on the femtosecond time scale, which should be more than adequate. And then we can start applying all our techniques. We know how to align molecules in the gas phase. We do that all the time in our laboratory. So we can actually hold the alignment of a molecule to a certain extent, or use other techniques to orient it. In conventional electron diffraction, that's not possible.
Another question before we go on?
Early on, you showed a timer. I think that was a rescheduling time that you actually measured, you said, by looking at the rabbit traces.
In the rabbit trace, I'm sorry, for the diffraction experiment? No, the diffraction is not rabbit. The diffraction is purely measuring the momentum of the electron. Okay? So the time there is, so we limit ourselves, as I just said, to a small range of k. Okay? And that corresponds classically to a certain return time. Okay? So that fixes a point on my time axis based on the color. And now we varied the color, did the analysis at the same energy, and that gives us time, right?
Or is time zero? What does time
Well, we
zero
can't measure time zero in effect. I mean, for time zero, we would have to look at very short trajectories, which we can't analyze in that region of non-scattered electrons. There's too much contributions from electrons that are not interacting with the structure, the molecular structure.
Of course, you can only measure time intervals. from the
Yes.
time there. But then you're inferring from a momentum distribution, you're inferring a time, a double time.
Yeah. Yeah, think about that momentum distribution, right? At different energies, classically, at different energies, so the electron classically is born at a particular phase. That takes me off the origin of my momentum distribution by the vector potential. So that defines now a new center. And now the length of that, I sweep a circle, the length of that circle, or the radius of that circle, is the rescattered energy. So the detected momentum is equal to the rescattered momentum plus the vector sum with the vector potential, right? Right. And there's a time, right? I can write a time into that.
So back to this business of trying to see simple molecules with your effect. Cesium dimers then might be interesting. We can think of a bigger core,
Yes.
a very simple system. You didn't do cesium because you can't get the density high enough?
No, I think, I mean, perhaps our technique is not very selective. So to get pure cesium dimer would be a challenge, right? There would be monomers in there, perhaps a little trimer. But I'll just quickly go back one. One thing we did try and is C60, okay, a fullerene that we can put into the gas phase. It's a more complex system. It's highly symmetric. And what we're seeing is, at this point, we can get the long-range distance. That is, we can get the size of that cage, which is about 7 angstrom. We're very confident now with this broad-banded approach that we can actually measure the classes of distances, like the carbon-carbon distance. We may not be able to distinguish between the pentagon distance and the hexagon distance, but that's okay because really this tool is the study dynamics, right? So what we want to do is excite the system and watch the bond change. Now, in that case, I think, you know, we have a powerful tool. And think about it. I mean, you know, we kind of imagine that, okay, we know how to make attoseconds. So we can follow all the kind of relevant dynamics from the electron out to the nuclei using a combination of these techniques.
Well, let's thank the speaker one more time.